Welcome to today's deep dive. I am so thrilled you are joining us today because we are heading into this glowing, buzzing, almost magical world of artificial light.
It really is a fascinating topic.
It is. Specifically, we are exploring the Wikipedia article on gas discharge lamps.
Yeah.
And our mission for this deep dive is to basically decode the hidden world inside the neon signs, the street lights, and, those fluorescent tubes that have quite literally illuminated our modern nights.
Yeah, and when you think about it, we spend an enormous fraction of our lives bathed in this very specific type of light.
We really do.
But very few of us actually stop to think about what is, happening inside those glass tubes. I mean, it represents this incredible intersection of chemistry, physics, and engineering that honestly took centuries to perfect.
Exactly. So I want you, the listener, to picture a classic buzzing neon sign glowing in a diner window. Or maybe that stark, intense yellow glare of a parking lot streetlight late at night.
Oh yeah, that classic yellow hum.
Right. We tend to think of these just as light bulbs, but they aren't. Not really. What you are actually looking at are tiny, completely controlled lightning storms happening continuously inside sealed glass tubes.
That is a perfect way to visualize it. It is captured, sustained lightning.
Wow.
And the sheer variety of ways we have figured out how to create and control these miniature storms over the centuries, it's a profound testament to human curiosity and really our desire to conquer the dark.
Okay, let's unpack this, because the core physics of how these lamps actually work is just mind-blowing.
It really is.
First, let's just define what a gas discharge lamp actually is. So, according to our source, it is an artificial light source that generates light by sending an electric discharge through an ionized gas,
Right.
which turns that gas into a plasma.
Okay.
Now, I know the standard ingredients are noble gases, things like argon, neon, krypton, or xenon. But I noticed the source mentions manufacturers also adding solid materials to the tubes,
Yes, they do.
like sodium or metal halides. Why put solid metals inside a gas lamp?
Well, those extra substances are crucial for specific lighting effects. And the thing is, they don't stay solid for long.
Oh, they don't?
No. During the startup phase of the lamp, the internal temperature spikes massively. This heat causes those solid metals to vaporize and basically become part of the gas mixture itself.
That sounds intense.
It is.
Yeah.
Containing that intense reaction requires some serious hardware. I mean, some of these lamps use a fused quartz or a borosilicate glass tube that is heavily insulated with a mica disc,
Just to handle the heat.
just to keep the sheer heat and pressure from melting the fixture entirely.
So you have this heavily fortified glass tube filled with a specific cocktail of gases and vaporized metals. What is actually happening at the atomic level when you flip the switch?
So when you apply an electric field between the two electrodes inside the lamp, that's the anode and the cathode, the force is so strong that some electrons are literally ripped away from the gas atoms near the anode.
Just torn right off.
Exactly. This strips the atoms of their negative charge, leaving them positively ionized.
So you suddenly have these two different groups of particles moving in opposite directions at incredible speeds.
Correct.
The free electrons, which are negatively charged, go rushing toward the anode. Meanwhile, the cations, which are the atoms that just lost an electron and are now positively charged, get accelerated by the electric field and rush in the exact opposite direction.
Toward the cathode, yes. And it is a chaotic, incredibly crowded space inside that tube.
I can imagine.
Those rushing ions usually only cover a microscopic distance before they violently crash into neutral gas atoms.
So they're just slamming into each other.
Over and over. And during these collisions, the anions forcibly take electrons from the neutral atoms.
It's basically a game of atomic bumper cars playing out millions of times a second.
That's exactly what it is.
They crash into each other and swap parts. The atoms that just lost an electron during the collision become ionized themselves, and they speed off toward the cathode to continue the cycle.
But wait, what happens to the ions that gained an electron during the crash?
That is the critical moment of illumination.
Really? Yeah. When those ions gain an electron, they are forced to return to a lower energy state. And physics dictates that energy cannot just disappear into nothingness.
Right, conservation of energy.
Exactly. So as they drop to that lower energy state, they release that leftover excess energy in the form of photons.
Photons, which is light.
Yes.
So that characteristic glow of a gas discharge lamp is literally the visual evidence of billions of ions dropping to a lower energy state after an atomic collision.
You got it.
Electrons are essentially being relayed through the gas from the cathode to the anode and lighting up the night in the process. That is amazing.
It is an incredibly elegant system. However, it comes with some very strange quirks that baffle a lot of first-year physics students.
Oh, like what?
Well, unlike a normal electrical component, like a standard copper wire or the heating element in your toaster, most gas discharge lamps exhibit something called negative resistance.
Wait, normally if you push more current through something, the resistance increases or at least stays steady. Like pushing water through a pipe gets harder the more water you try to force through.
Right.
How does negative resistance work?
What's fascinating here is that the plasma behaves completely counterintuitively. In the plasma of a gas discharge lamp, as the current flow increases, the number of charge carriers, the ions and electrons, also increases.
Okay, so there's more stuff to carry the charge.
Exactly. This makes the plasma more conductive, so the resistance actually decreases.
Wow.
It gets easier and easier for the electricity to flow the more electricity you add.
Wait, but I plug my neon sign in at home all the time. If the resistance drops as the current goes up, what is stopping it from drawing infinite power?
Nothing, naturally.
So why doesn't it go into a current runaway and just explode in my living room?
It absolutely would if you plugged the raw tube straight into a wall socket.
Seriously?
Oh, yeah. Within a fraction of a second, the current would spike exponentially, creating an arc flash that would destroy the lamp and blow your fuses.
That sounds dangerous.
Which is why every single one of these lamps requires auxiliary electronic equipment called a ballast.
A ballast.
Yes, the ballast acts as a governor, strictly limiting and controlling the current flow through the gas, keeping that runaway destruction from ever happening.
So every time you see a fluorescent light flickering on in a quiet office building, there is a hidden, complex piece of technology working overtime just to keep the whole thing from exploding.
Pretty much.
That is incredible. But what I love about this source is that it points out this isn't some brand new modern invention.
Not at all.
The history of this technology is full of bizarre accidents. Like, let's rewind all the way back to the year 1675 with the French astronomer Jean Picard.
Right, and 1675 is well before the invention of the commercial light bulb.
Oh, totally.
Long before the electrical grid, or even a basic understanding of atomic structure.
So Picard was walking around at night carrying his mercury barometer, and he noticed that the empty vacuum space at the top of the glass tube was mysteriously glowing as the mercury sloshed around inside.
It must have seemed like absolute witchcraft at the time.
Seriously?
Because what he was witnessing was static electricity generated by the physical friction of the moving mercury, discharging through the low-pressure mercury vapor in the empty space of the tube.
Wow.
It was the very first recorded observation of a gas discharge light.
And naturally, people became obsessed with figuring it out. By 1705, a man named Francis Hauksbee took this accidental observation and engineered it into something practical.
He did.
He used static electricity and a partially evacuated glass globe with a little bit of mercury inside. And when he charged it, it produced a continuous light that was actually bright enough to read a book by.
Which was a monumental leap forward.
Yeah.
And throughout the early 1800s, scientists like Vasily Petrov in 1802 and Sir Humphrey Davy at the Royal Institution in 1809 pioneered the continuous electric arc.
Taking it even further.
Right. They proved you could sustain this kind of light if you just had enough continuous electrical power. But the application of this technology took a very strange, almost sci-fi turn in the 1860s.
I loved this part. If you have ever read Jules Verne, specifically Journey to the Center of the Earth or 20,000 Leagues Under the Sea, you might remember the characters using something called a Ruhmkorff lamp to see in those extreme environments.
Yes, the famous Ruhmkorff lamp.
Verne wrote about it like it was the ultimate futuristic, almost magical gadget.
And in the context of the 1860s, it really was cutting-edge technology. But Jules Verne didn't invent it.
No, he didn't.
It was actually developed by a fascinating real-world duo, an engineer named Alphonse Dumas, who worked at the iron mines in France, and a medical doctor named Camille Benoit.
What a pair.
In 1864, they actually won a highly prestigious prize of 1,000 francs from the French Academy of Sciences for this invention.
An engineer and a doctor teaming up to make a sci-fi lamp. It sounds like the setup for a great movie. But what was the actual practical use driving this invention?
Well, they needed a light source for incredibly dangerous, volatile environments. Think about a coal mine in the 19th century. It is frequently filled with explosive fire damp gases. A single spark from a pickaxe or an open flame lantern was an absolute death sentence. They desperately needed a lamp that was completely sealed off from the outside air.
That makes total sense.
So the Ruhmkorff lamp used a Geissler tube, an early cold cathode tube. excited by a battery-powered Ruhmkorff induction coil.
So they can carry it around.
Exactly. This coil was an early transformer that converted low-voltage direct current into rapid high-voltage pulses to excite the gas safely inside the glass.
It was perfect for those explosive mining environments.
Yeah.
But also for diving, since it didn't need ambient oxygen to burn.
Right.
And because it was a heatless lamp, Dr. Benoit saw its immense potential for use in surgery, where hot lanterns were a major hazard.
Absolutely.
But the evolution of how they lit these things is my favorite part of the story.
It's a great example of trial and error, because the early versions of the Ruhmkorff lamp used carbon dioxide in the tube because it generated a brilliantly bright white light.
Sounds ideal.
It does, but the carbon dioxide had a fatal chemical flaw. Under the constant, intense electrical discharge, the gas molecules tended to break down over time.
Oh, no.
Yeah, eventually ruining the lamp and leaving the miners in the dark.
So Dumas and Benoit had to improvise. They swapped the carbon dioxide for nitrogen. And nitrogen is far more stable, but it doesn't glow white. It glows a deep red.
Which is a problem.
Yeah, a dim red light isn't exactly ideal for seeing clearly in a pitch-black mine shaft or during a delicate medical surgery. So to fix the color problem, they replaced the standard clear glass tube with uranium glass.
And uranium glass possesses a very specific property. It fluoresces. When the red light from the nitrogen discharge hit the uranium glass, the glass itself absorbed that energy and fluoresced with a bright green light.
It is a brilliant, highly resourceful example of 19th century problem solving.
Truly.
And that clever use of uranium glass by Dumas and Benoit wasn't just a quirky fix. It was the realization that we could manipulate these atomic emissions.
That's the real breakthrough.
Here's where it gets really interesting. The rainbow of gases we use today. You see, the color of the light produced by a gas discharge lamp isn't random. It depends entirely on the specific emission spectrum of the atoms making up the gas.
Right. Every single element on the periodic table has a unique atomic structure, and therefore a completely unique emission spectrum.
Like an atomic fingerprint.
Exactly like a fingerprint. When those electrons we talked about earlier drop down in their energy state, the specific color of light they emit is the exact visible measurement of the distance between that atom's energy shells.
That is wild.
It's visible quantum mechanics.
Let's look at some of the famous examples from the source. Neon is legendary for producing a brilliant, intense red-orange light.
Classic neon.
Right. Argon, on the other hand, gives off a violet to pale lavender blue color. But then you have mercury vapor, which is a bit of a trickster.
It is. Mercury vapor naturally emits a light blue color, but more importantly, it produces an intense, massive amount of ultraviolet radiation.
Which we can't see.
Exactly. Human eyes cannot see UV light. So on its own, a pure mercury vapor lamp isn't very useful for general lighting. Most of its energy is completely invisible to us.
But engineers are clever. Just like Dumas and Benoit used uranium glass to change the red light to green, modern engineers line the inside of the glass tube of a mercury vapor lamp with a specialized fluorescent coating.
Yet the white powder you see inside the tube.
That coating absorbs the invisible UV radiation and instantly converts it into bright, visible white light. That is exactly how the fluorescent tube in your office or the curly bulb in your kitchen actually works.
And this specific method of conversion brings us to a crucial concept in lighting design, the color rendering index, or CRI.
The CRI.
This is a standardized measure introduced by the International Commission on Illumination. It basically evaluates how well a light source reproduces the true, accurate colors of physical objects compared to natural sunlight.
And this is where some gas discharge lamps, despite being powerful, really struggle to do their jobs well.
Take the low-pressure sodium lamp as a prime example. It is phenomenally efficient. I mean, it can produce up to 200 lumens per watt, making it the most efficient gas discharge lamp type in existence.
That's a lot of light for a little power.
But the downside is that it produces an almost monochromatic, piercingly bright orange-yellow light.
I know exactly the light you mean. It is the kind of street light where you park your car to go to a concert, and when you come back out, you literally can't tell what color your car is.
Oh, absolutely.
A red car looks black, a blue car looks gray. Everything just looks washed out in this dystopian orange filter.
That phenomenon happens because low-pressure sodium lamps have a terrible, almost non-existent CRI because they only emit light in a very narrow yellow wavelength. They simply lack the other color wavelengths needed to reflect off your car and back to your eye.
That makes perfect sense.
That is why they are really only acceptable for street lighting or security perimeters, where spotting a moving shape efficiently is much more important than color accuracy.
Okay, so that covers the low-pressure family. We have low-pressure sodium. We have standard fluorescent lamps, which operate at a tiny fraction of atmospheric pressure, about 0.3% of the pressure at sea level. We also have classic neon lighting in this category. Oh, and I have to mention the flicker flame bulb.
Have you seen these in novelty shops?
Yes, the novelty bulbs that look like a flickering physical candle flame. The engineering behind a cheap novelty item is so wild to me.
It's surprisingly complex.
To make that flickering candle effect, they use a mixture of neon, helium, and a little nitrogen gas. The electric current passes through two flame-shaped electrode screens.
Right.
And they coat the screens in a chemical called barium azide, which essentially acts as a chemical catalyst, making the electron jump erratic and unpredictable.
So the plasma jumps around.
Exactly. The ionized gas moves randomly back and forth between the two electrodes, creating that chaotic dancing flame effect.
It is a wonderful example of intentionally utilizing the volatile, unstable nature of plasma for aesthetic purposes.
Just for fun, basically.
Yeah. Now, moving up from the low-pressure realm, we enter the domain of high-pressure discharge lamps. In these fixtures, the gas is kept anywhere from slightly less than standard atmospheric pressure to much, much greater pressures.
The source mentions that some modern automotive high-intensity discharge headlamps operate at up to 50 bar.
That's huge.
That is 50 times the pressure of the Earth's atmosphere contained inside a tiny superheated glass bulb in the front of your car as you drive down the highway.
And in this high-pressure category, you have high-pressure sodium lamps, which are still used extensively for streetlights, but boast a much broader spectrum than the low-pressure ones, making colors a bit easier to distinguish.
So no more green cars.
Right. They're also heavily utilized in agriculture for artificial plant growth. You also have metal halide lamps, which give off a crisp, piercingly bright white light.
I think I've seen those.
Those are the massive lights you see illuminating tall skyscrapers, nighttime sports stadiums, and sprawling commercial parking lots.
And at the absolute top of the power scale, you have the high-intensity discharge, or HID lamps. These things are absolute monsters of illumination.
They really are.
They use incredibly thick tungsten electrodes housed inside fused quartz or aluminum arc tubes, simply because the raw heat and power are just too intense for regular glass to survive.
Because the power density is the defining characteristic of HID lamps. The electrical arc power is exceptionally high relative to the physical length of the arc.
Right.
They are deployed when you need absolutely massive, overwhelming amounts of light concentrated into a small space.
The perfect example from our source is the IMAX projector.
Oh, that's a great example.
To throw a crystal clear image onto a screen that is several stories tall, they don't just use a big light bulb. They use a 15 kilowatt xenon short arc lamp.
15 kilowatts.
Think about the atomic bumper cars happening inside that tiny tube. The pressure is immense. The heat is staggering. It is a contained inferno of blinding plasma sitting right there in the projection booth.
If we connect this to the bigger picture, it is clear that we are actually in a period of profound technological transition.
Oh, so?
Well, the source explicitly notes that highly efficient white LED lamps, which now routinely achieve between 61 and 200 lumens per watt, are largely replacing gas discharge lamps in many everyday applications.
LEDs are everywhere now.
They are. LEDs are solid-state technology. They don't rely on contained plasmas, pressurized gases, or delicate glass tubes.
They are simpler, often much safer, and incredibly efficient over long periods. But it feels important to acknowledge that the era of the gas discharge lamp isn't just a footnote in the history of technology.
Far from it. A century of intense global research into how to excite gases, how to control volatile plasma, and how to harness specific atomic emission spectra paved the way for so much of our modern understanding of quantum physics, material science, and commercial lighting.
It's foundational.
We simply wouldn't have modern LEDs without the foundational science learned from tweaking those early Geissler tubes and room core lamps.
So what does this all mean? Well, I hope that the next time you take a walk down a city street at night, you don't just see a mundane collection of bright bulbs keeping the dark at bay.
You're seeing science in action.
You are walking through a gallery of invisible atomic physics. Every low hum of a neon sign, every stark shadow cast by a metal halide stadium light is the direct result of electrons being violently stripped collided, and dropping energy states, releasing quantum photons just for you to see your way home.
And there's one final, incredibly fascinating detail hidden at the end of this source that points to where this technology went next. And it feels like science fiction all over again.
What's that?
The article mentions that 100 years of research eventually led to the creation of gas discharge lamps that don't even use electrodes.
Wait, no electrodes. How do you excite the gas into a plasma without an anode and a cathode physically inside the tube?
They are energized externally using powerful microwave or radio frequency sources. The invisible energy field simply passes right through the glass envelope and excites the plasma inside without any physical electrical connection to the gas itself.
Now that is something to think about. I want you to ponder what that means for the future. If we can excite gases into emitting brilliant light just by using ambient radio frequencies or microwaves without needing wires or metal plugs directly touching the gas,
It changes everything.
could the future of lighting be entirely invisible fields? Imagine a world where the glowing bulb itself disappears completely in carefully tuned, invisible energy fields turn the very air or the objects around us into a canvas of light.
It certainly redefines our entire concept of what a light fixture can be, and it shows that our journey to control light is far from over.
It really does. Thank you so much for coming on this journey through the plasma-filled history of illumination with us today. Keep looking up, keep noticing the fascinating details hiding in plain sight, and above all, keep questioning the world around you. We'll catch you on the next deep dive.